This year, the Nobel Prize in Physics is directly related to black holes. Specifically, it was given to astronomers who discovered the Milky Way's central black hole, and to Roger Penrose, who proved that, according to general relativity, every black hole contains a region of infinite gravity, that is a singularity. Penrose's theory of singularity has a much deeper significance than it appears. It forces us to test the limits of Einstein's theory and also to think about the origin of the universe. Black holes have always, like ghosts, lingered on the fringes of scientific thought since the 1700s. When John Michell and Pierre-Simon Laplace studied Newton's law of gravity, they realized the possibility of objects so massive that even light could not escape their surface. Very few took these black stars seriously, especially considering that, in reality, light does not behave as described in the works of Newton, Michell, and Laplace. And after all, gravity doesn't work the way the great Newton, or Newton as you prefer, described it either. In 1915, Newton's theory was essentially replaced by Einstein's general theory of relativity. And that wasn't the end of the story about black holes, or black stars as they were called. It was just the starting point for their study. Carl Schwarzschild solved the general relativity equations shortly after Einstein published them, and he proved that a very dense sphere of matter would be surrounded by a surface where time itself would come to a stop. Below this event horizon, all matter, light, and space are doomed to fall inward toward the central point. In this so-called singularity, the gravitational field becomes infinite. Physicists often question infinities, as they're usually theory errors rather than actual facts. Einstein himself doubted that black holes could form in the real universe, and even if they could, it would be without singularities. In 1939, Robert Oppenheimer and Hartland Snyder showed that a perfectly spherical dust ball could collapse into a Schwarzschild black hole, including singularities. That makes sense because if all the particles are falling straight toward each other, according to the math, they should all land in the center. But that didn't convince anyone. Indeed, where in the universe can you find something spherical and so perfectly smooth? It was decided that ordinary objects could never collapse into a perfect point. The slightest deviation from spherical symmetry, and the particles don't fall onto each other, and they're not pulled to the center. Now we've moved on to 1960. Roy Kerr had just come up with the idea of how to describe a rotating black hole in Einstein's theory. In it, the central point of infinite gravity is twisted into a ring, but it was still a singularity. Kerr's solution was still extremely symmetrical, so the old doubts about their existence in objective reality didn't go away. This is what led a young Cambridge physicist named Roger Penrose to prove that black hole singularities were absolutely inevitable in Einstein's theory. Penrose's scientific paper on singularity is surprisingly short, just a couple of pages in a journal. As they say, brevity is the soul of wit. Some people believe that this 1965 paper was the first serious addition to the general theory of relativity in the entire half-century since its creation. Albert Einstein. What did Penrose discover? How did he manage to mathematically grasp the essence of a black hole? And finally, why did he deserve the Nobel Prize? Roger Penrose proved that, according to Einstein's theory, with a couple of assumptions, black holes must contain singularities. And he did this by demonstrating a space-time grid that literally comes to its end inside a black hole. In general relativity, we denote spatial coordinates using geodesic curves. The path of a light ray down into a black hole is called a null geodesic line, or simply a geodesic. This is a kind of gold standard for marking out space-time. Null lines are traced through or across a gravitational field, gradually converging to a single point. This is called gravitational lensing. Gravitational fields created by ordinary matter always produce this convergence. It would take negative mass or negative pressure for the rays to start diverging. This feature of gravitational fields is called the weak energy condition in general relativity. Thus, the null lines heading toward a black hole must converge. There doesn't seem to be anything complicated about this, but there's something strange. The null lines beyond the event horizon, moving outward, oddly enough, will also converge. The concept of the event horizon is ambiguous and varies with the observer's position. Regarding the black hole, Penrose proposed a clearer idea, the idea of closed surfaces. Any closed space inside a black hole is considered a closed surface. Penrose stated that at least several parallel rays of light leaving a closed surface, moving either up or down, must converge. In other words, space and time end at the focal point. Let's try to compare this with a more familiar type of geodesy. On planet Earth, we use parameters such as lines of longitude and latitude. The line of longitude converges at the north and south poles. Such a line is the shortest route from one pole to the other, but you can get a bit carried away, miss one of the poles, and start circling the planet again. That way, it will no longer be the shortest route. Traveling through a black hole, you won't reach any poles, but you will reach the end of time or space. A kind of dead end of reality. Roger Penrose was able to show that space and time can have peculiar holes. These holes are directly related to infinite space-time curvature or infinite gravity. In other words, singularities. Penrose was not able to show what type of singularity would form in a black hole. He only found out that its presence there is inevitable. As soon as Penrose published his work, a young student was inspired and complimented this work in a very unusual way. The student's name was Stephen Hawking. In his doctoral thesis, Hawking demonstrated that we can use the same proofs to determine the behavior of geodesics, moving backward through our entire universe to the Big Bang. We've known for about 40 years that the universe is expanding and that it most likely originated in a much less compressed form. We know that geodesics converge as they move backward in time, but that doesn't mean that each of them necessarily has to meet another. For example, they might miss each other but still form a dense knot. Hawking shows that Penrose's evidence regarding black holes also applies to the universe. Geodesics, moving backward in an expanding universe, must actually converge, forming a singularity. Time itself cannot be traced beyond this point, which suggests that time actually began at the moment of the Big Bang. Hawking and Penrose later developed these ideas together, publishing them in 1970. It's probably the right time to say that the singularity theorems are most likely incorrect, or at least lead to incorrect conclusions. They give us predictions from the pure theory of general relativity and take into account various energy conditions. We know that general relativity is not the complete picture, and in fact, this understanding is the greatest achievement of the singularity theorems. The solution might be a union of general relativity and quantum mechanics, a theory of quantum gravity. Such a theory could really tell us what actually happens to geodesics when they collide, and we would even like to believe it. What are geodesics really? Space and time? Penrose and Hawking have given us a roadmap to this as yet unrevealed theory. Roger Penrose received the Nobel Prize in Physics this year for his contribution to the theoretical understanding of black holes. He shared his award with Andrea Ghez and Reinhard Genzel, who proved the existence of a supermassive black hole at the center of the Milky Way. By studying the orbits of stars in the central region of the galaxy, the work of Ghez, Genzel, and other astronomers confirmed the existence of black holes, which means that there are actually places in the universe where the general theory of relativity must allow for the existence of singularities. And all these incredible discoveries came from the idea of how rays behave when they collide and end up in the dead ends of space-time. The moon, so mysterious, alluring, and enigmatic. The only satellite of Earth, its eternal companion. It seems that it has already been studied inside and out. People and probes have landed on the moon. Scientists have already held samples of lunar soil in their hands, and they've even tried to grow some Earth plants there. The dark side of the moon has long ceased to be a mystery, and overall we know almost everything about it. But what questions does humanity still have? What if these questions are actually the most important ones for us? After all, the moon's influence on Earth is much greater than you think. And it's not just limited to the connection with insomnia during the full moon, as you might be used to thinking. What if we try to answer the most important questions about the moon? How did the moon actually appear? And why are there samples of Earth's rocks on its surface? Is it really true that without the moon, life on Earth might not exist at all? And what if instead of the moon, there were other planets from the solar system? Buckle up! We're traveling through time to see a planet that hasn't yet seen humanity, to witness a cosmic scale catastrophe that may have sparked life on Earth and given us our satellite, and to find out just how important the moon's influence has been on our Mother Earth. To begin with, let's recall what we know about the moon. The moon is a relatively large satellite compared to the size of its planet. Its diameter is 3,474 kilometers, while the Earth's diameter is 12,742 kilometers. Such proportions are very rare in the solar system. Only Pluto has a truly large moon, but Pluto recently lost its status as a full-fledged planet and became a dwarf planet. As for Earth, planetary scientists believe that the moon stabilizes our planet's orbit, and in particular the tilt of its axis of rotation, which creates the seasons. Some believe that without the moon, the tilt of Earth's axis of rotation could have changed significantly over several million years. This would have led to unstable climate conditions, making the environment less favorable for the development of life. In addition, the presence of the moon increased the length of the day. Let's not forget that the moon, thanks to its reflective ability, provides us with light at night, and its magnetic forces help regulate the level of the world's waters. The Apollo program made a huge contribution to our study of the moon. Lunar soil samples were brought back to Earth, a real treasure trove for those who truly wanted to learn more about the origin of our satellite. One of the most amazing discoveries scientists made in this area was the fact that the composition of this soil strikingly resembled the composition of the Earth's outer rock layers. For example, if you take an element like oxygen and look at the prevalence of its isotopes, you can conclude that their composition is almost identical in lunar and Earth soil. But if we try to compare terrestrial soil and say Martian soil, their composition will be radically different. Another important discovery was that lunar rock is much drier compared to terrestrial rocks. It seemed that lunar rock had been exposed to extremely high temperatures and had lost elements that are prone to easy evaporation. What could this mean? Could it really be that the moon was once a part of the Earth? Moreover, this suggests that the process of the moon's formation is connected to some extremely destructive event, namely the collision of our Earth with a massive celestial body. Could it really be true, and is that how the moon actually appeared? There are several theories about how the Earth acquired its faithful pale companion, but the most likely one is called the giant impact hypothesis for the moon's formation. According to this hypothesis, several billion years ago, an object comparable in size to Mars collided with our planet. since the impact was glancing, otherwise the Earth would have simply exploded. This object either bounced off into space after hitting the Earth, or it was completely absorbed, sinking inside. Chunks of magma rock that were ejected by the Earth as a result of the impact ended up in Earth's orbit. And there, over millions of years, they came together into a single object, which, thanks to its rotation, took on a spherical shape. But what if this collision had never happened? And what if there had been people on the planet at that moment? Let's go back about 4.6 billion years when hundreds of very young planets began to form around a new star, our Sun. Among them were the little ones, Venus and Earth. Their orbits were very different from what they are now. They were more chaotic, so collisions were bound to happen. Imagine a race with no rules. A bunch of cars with different speeds are driving in circles, in our case, around the young sun. They overtake each other and crash into each other very often. Earth and Venus succeeded in this race. They became true devourers of smaller planets. These planets were similar at the very beginning of their life journey, but something happened that made the two sisters completely different. And that something were collisions with other celestial bodies that Venus and Earth experienced, and which in fact forever changed the destinies of the two worlds. So, two objects crash into Earth and Venus, and both of these impacts have huge consequences for both planets. So what happens? The impact that happened to Earth makes the planet spin faster. It spins it up. Because of this, a strong magnetic field forms around the planet, which gives the planet protection from most of the solar radiation. This is what allowed life to develop on Earth in the future. Thanks to this impact, the Earth gained its axial tilt, causing the change of seasons. Could it be that the same thing happened to Venus, and life could have formed there as well? Unfortunately, no. When a larger, similar object crashed into Venus, its impact not only managed to stop Venus's rotation, but it also made the planet start rotating in the opposite direction. Also, its rotation is nearly 243 times slower than Earth's. How could this catastrophe have affected the future of Venus? The thing is, the planet's rotation speed became insufficient for its core to start generating a strong magnetic field. As a result, the surface of Venus was left defenseless against the deadly stream of particles shot out from the sun. The hypothetical planet that knocked a chunk out of Earth, which later became the Moon, is called Theia. It is believed that the collision between Earth and Theia was the last major catastrophe our planet experienced. Can you imagine what would happen to us if a planet of that size collided with Earth today? One thing can be said for sure: humanity would have no chance of survival. A wave of fire would completely burn up the atmosphere. Pieces of the two planets would later begin to form a new world, one that would have no place for humans or any forms of life that once inhabited Earth. I really wouldn't want to experience such a catastrophe, but in reality, we should definitely be grateful to Theia. After all, without the Moon, life on our planet would be drastically different from what we have now. Many experts even question whether life could have developed on Earth at all without a natural satellite with parameters similar to our Moon. This is part of the so-called rare Earth hypothesis, which we will definitely discuss in future episodes. In the meantime, let's try to imagine what it would be like if other planets of the solar system were in the place of the Moon. In the case of Venus, due to its large size and remarkable reflectivity, we would have nights comparable to our current early twilight. Also, Earth's sister couldn't become its satellite. She's simply too large. If Venus were to move around the Earth at the same speed as the Moon, sooner or later their trajectories would collide, and we would have a new catastrophe. Almost the same applies to Mars. If you were unlucky enough to be on planet Earth at the moment Venus or Mars became a natural satellite of our planet, you would have to prepare for one catastrophic consequence or another. Tsunamis, a sudden rise in sea level, and a catastrophic increase in the sunlight reflected by the satellite. Let's not forget about the changes in the trajectories of the two planets. Although in the case of Mars, some specialists allow for the possibility of Earth and Mars turning into a kind of mini planetary system, existing in a certain balance without collisions or large-scale cosmic catastrophes. And what will happen if the possible satellite is larger than Earth? Our planet, if it ended up at a short distance from Jupiter, would itself become a satellite of the gas giant. The terrifying gravitational force of the giant would destroy our planet, gradually crushing it and capturing it piece by piece. Almost the same fate awaits us in the immediate vicinity of Saturn. So we should be glad that it's our small and cozy moon that's next to us. What else has it done for Earth besides the very fact of its appearance? It's amazing, but some believe that our planet's satellite made a decisive contribution to our very existence. And it's not just about the catastrophe that made the Earth spin faster. How exactly? Remember that the moon is responsible for the tides of the world's oceans? Scientists believe that tides gave the initial push for life to emerge on Earth. When the substances present in the early oceans mixed with water, special conditions were created in the tidal zone. Then the water evaporates due to the sun. During high tide, the water would return and flood the rocks. In these conditions of wetting and drying of the rocks, something began to form that much later would become life. Under such conditions, very complex molecules appeared from simple substances. Ribonucleic acid, one of the fundamental components of living cells, could have first arisen thanks to the tides controlled by the movement of the moon. The tidal zones were real chemical laboratories of that time. Laboratories where life itself was being created. It may sound silly to a modern person, but after learning so many remarkable facts about our closest cosmic neighbor, it's not surprising at all that throughout the centuries, the image of the moon has been deified and celebrated in the culture of world civilization. But even now, we can look at the lunar disk or the moon with gratitude and curiosity. After all, who knows how many wonders are hidden in this mysterious celestial body, so close and yet so far away. Is it true that no one has ever been able to measure the speed of light? What nonsense, you might say. The speed of light is well known, isn't it? It's 299,792,458 meters per second. We learned this back in school. We're so sure about this that since 1983, we've used the speed of light to define the length of a meter. Actually, it's just the distance light travels in a vacuum in 1 second. The formula easily confirms this definition. 299,792,458 is the exact speed of light, with no inaccuracies or fractions. So what is our video about then? We will try to prove to you that light might not actually travel at that speed at all. Such a strange statement has the right to exist because, in reality, no one has actually been able to measure this speed. Let's imagine that we need to measure the speed of some object, for example, a ball. Let's say we shoot it out of some kind of cannon. To find out the speed of the ball, we need to know two parameters: the distance between 2 points that the ball will fly through and the time the ball will spend on this. So we take the distance, divide it by the time, and voila, we found the speed of the ball. Is it possible to measure the speed of light in such a simple way? Imagine you have a device capable of sending a beam through a perfect vacuum over a distance of 1 kilometer. You start the timer the moment you fire the beam and stop it when the beam reaches the 1 kilometer mark. There's a problem. How do you know when the beam has reached the boundary? All right, it seems we need 2 timers, one at the start of the beam's path and another at the end, which can stop automatically when it detects the beam. There's another problem. How can we be sure that both timers are synchronized? For example, we could connect them with a wire and send a signal from one device to the other, but this signal will travel at the speed of light, which means it will arrive with some delay. Let's try another way. We'll combine and synchronize 2 timers and then send one of them to the border. What could go wrong? The special theory of relativity states that moving clocks tick slower compared to stationary observers. By the time the clock reaches the 1 kilometer mark, it will no longer be synchronized with the device that was left behind. There is only one solution to this problem. Forget about the second timer. Let it travel through the vacuum. Let's place a mirror 1 kilometer away from the first timer so it can reflect the beam. In that case, the first timer can detect the returning beam and stop. However, it will have measured 2 kilometers instead of 1. The description of this experiment is very similar to the first attempts to experimentally measure the speed of light. The French physicist Hippolyte Fizeau, in 1849, shone a light toward a mirror located 8 kilometers away from him through a rapidly rotating cogwheel. By increasing the speed of the cogwheel's rotation, he managed to make the light beams return back, passing through the paired rows of the cogwheel's teeth. It was then found that the speed of light is 313,000 kilometers per second. Notice that that's only 5% off from the modern value. Can we call this experiment successful? Essentially, the round-trip path of light was measured, but no one has managed to measure the one-way. But think about it. What if the speed of light in one direction is different from the speed of the returning beam? Imagine that we need to talk to a cosmonaut who is currently on Mars. Most likely he will have an American name, but for convenience we will call him Misha. We send him a signal and get a response 20 minutes later. That is, our signal takes 10 minutes to reach Misha, and then it takes another 10 minutes for his reply to come back. That sounds pretty logical. But how about the hypothesis that our signal takes the whole 20 minutes to reach Mikhail, but his reply arrives instantly? Nonsense. Nonsense. From a scientific point of view, both of these versions have the right to exist. How should the speed of light be different? Perhaps there is a more convenient route through space-time, a kind of express highway in matter. That makes sense because, in addition to symmetry, there is a huge amount of asymmetry in the universe. Scientists are still trying to understand why there is more matter than antimatter in our universe. Physicists often assume that the speed of light may be different depending on whether the beam is moving forward or trying to go back. This difference could be just a few percent, or it could reach extreme values, up to infinity. Our knowledge of the exact speed of light is actually an agreement rather than an experimentally proven fact. Albert Einstein pointed this out in his work published back in 1905 titled On the Electrodynamics of Moving Bodies. Several pages of the work are devoted to the problem of synchronizing clocks in different locations. Einstein writes that there is no way to consciously compare 2 quantities with each other until we agree on how much time it takes for a light beam to make the return trip. Thus, the term Einstein synchronization appeared in science. Essentially, it is an agreement for synchronizing clocks located at different points. For 100 years, scientists have tried to calculate the speed of light by itself, without mirrors and reflections. Could it really be that in all that time, people haven't come up with a way to finally do it? Can we, for example, use a high-speed camera that can take 1 trillion frames per second? That way, we could see how light travels through some kind of hollow container. The problem is that with a camera, you don't see the light itself. You see its reflection on the lens. Again, that's not the one-way path of light, but the path there and back. Let's go back to our old experiment with 2 timers. We sent one into a vacuum. Let's bring it back. So what if we put a synchronizing device between these 2 timers, connect it to the timers with a wire, and send them 2 simultaneous pulses? If the speed of light is the same in both directions, then the clocks will be perfectly synchronized. But if the speed of light is different, one clock will get ahead of the other. It turns out that from this difference, you can extract that very magical value of the speed of light. But even then, it still won't be considered the speed of light. For this very reason, synchronizing clocks using this method won't work. The whole system is based on the assumption that the speed of light is the same in all directions. What if we try placing 2 synchronized timers in the middle of the route and start moving them in opposite directions? Again, this will only work if the speed of light is the same in both directions. There's a dilemma here. We need synchronized clocks to calculate the one-way speed of light, but we need to know the one-way speed of light to synchronize the clocks. If we can never calculate the one-way speed of light, then why talk about it at all? Some scientists cite Occam's razor as an example. This is the name of a methodological principle which states that one should not multiply entities beyond necessity. In other words, to put it briefly, it's much simpler and more convenient to accept as a fact that light travels at the same speed in all directions. And the most paradoxical thing is that science actually feels much better this way. If we just left this question open and couldn't give an exact value for the speed of light. It's important to call the truth what it is. The speed of light is a convention, not an empirically verified fact. Besides, how many interesting questions this realization can raise. When will now happen on Mars? Do events that happen at the same time in different locations really occur simultaneously? You might say these are all rhetorical questions, and we would agree. Yes, there is still no definite answer to these questions. But what if, after some time, modern science comes to understand these universal processes? Is it possible that space and time, the theory of relativity, and quantum mechanics are really connected? They are currently in contradiction. Just imagine that after some time we will know these facts through verified scientific methods and wonder how we didn't realize them right away. It was so obvious. We will leave you with these thoughts. We hope you enjoyed our video and will give it a like. At the speed of light, even though, as it turns out, it's not an entirely precise value. See you soon in a new, interesting video that will lift another veil separating us from understanding the laws of the universe. Subtitles created by